Hello everyone, Mr. Fawcett here, and we are back with another AP Calculus lesson. Today we start talking about derivatives of other exponential and logarithmic functions. And when I say other, I mean exponential functions and logarithmic functions that do not have a base of e. We've worked with the natural exponential function e to the x. As far as taking derivatives, we've done the natural log of x or ln of x as far as derivatives go, but we haven't looked at how to take the derivative when we have different bases. Let's look at this introduction question first before we actually get into how to take those derivatives. Maybe it's the same process we've been working with, maybe it's different, but we'll figure that out in a second. First, let's answer the introduction. It says, what was special about the function f of x equals e to the power of x when it came to its derivative? So go ahead, pause the video, write down what you know about that derivative. Well, we know that the derivative of e to the x, so f prime of x, is also e to the x. This function's quite not ordinary, out of the ordinary, I guess, in that the rate of change of the function at any specific point is equal to the value of that function, is equal to the y value. A very special property of the function e to the x. Let's see if this holds true for other exponential functions. So we see down here, our base is 2 instead of e. So let's think about what we could do as far as taking the derivative goes. And maybe pause the video, and if you think you have an idea, write it down. Well, maybe one idea that you thought of first was, well, I can just apply the power rule here, and I'll get f prime of x is equal to x times 2 to the power of x minus 1. It's a thought, for sure. It would be an incorrect one, though. Let me give you a quick visual proof as to why. Let's say I just sketch the graph of 2 to the power of x. So it's got that horizontal asymptote on the x-axis and a y-intercept of 1. And the function is always increasing, which means our derivative should always be positive. But I think it's pretty clear to see, right? If I substitute in a negative value for x here, I'm going to get a negative derivative, which wouldn't make sense because based on what we know about the characteristics of this exponential function, the derivative should always be positive because the function is always increasing. So that rules out the power rule. You actually can't use the power rule when your exponent is a variable anyway. But again, rather than just telling you that, why not show you visually why it wouldn't work? Turns out there's some tricky algebraic manipulation that we need to perform here. I guess not tricky, but tricky in the sense that I don't think it's obvious when you first look at this function and you think about what we need to do to take the derivative. So buckle in and look at the math magic at work. I'm going to rewrite this function as f of x is equal to e to the power of natural log of 2 to the power of x. Now, hopefully we can see that those are equivalent, right? The natural exponential function, natural log function, those are inverses. So this would simplify to 2 to the power of x. You may say, why are we doing this? What's the benefit? Now it actually looks more complicated when it comes to taking the derivative. It actually makes it a little bit easier for us, though. The one thing we have to do, though, is apply a property of logarithms. So I'm going to rewrite the function one more time. So I get f of x is equal to e. Now we have to remember that if I square the input of a logarithmic function, I can actually pull that out as a coefficient. So I can have x times the natural log of 2. So I can rewrite it that way. And now I'd encourage you to pause the video and see if you could now take the derivative of f of x. Okay, so if I'm going to take the derivative, so I'm going to get f prime of x, well, this is going to be a chain rule, right? My outside function is e. When I take the derivative of e, well, nothing changes. I get e to the power of x times the natural log of 2. But now I have to take the derivative of my inside function. I've got to take the derivative of x times the natural log of 2. Well, this is just like if I was taking the derivative of x times 5 or 5x. The natural log of 2 is just some number. It's some coefficient. So just like the derivative of x times 5 would be 5, the derivative of x times the natural log of 2 would just be the natural log of 2. So this is our derivative. We can go ahead and simplify. Notice that this, right, is exactly what we started out with. I'm going to show you this in between step, but you obviously don't have to write it once you understand what's going on. I can rewrite it as e to the power of, natural log of x squared times natural log of 2. And then I can write this as, so it's 2 to the power of x, not x squared. There we go. I get 2 to the power of x times the natural log of 2. You may also frequently see it written the other way. So the natural log of 2 times 2 to the power of x. Obviously, both of those mean the same thing. There is your most simplified derivative of 2 to the power of x. Okay, let's jump to the next page real quick. Time for you to do some practice on your own. So based on what we did above, see if you can take the derivatives of both of these functions right here. And I would encourage you to go through all of the steps, practice that algebraic manipulation. One, it's just good practice with your algebra skills. But two, it will help you remember how to take the derivative of an exponential function if you forget. This is something we don't use nearly as much as the other common derivatives, so you're probably likely to forget the formula, which is not a big deal if we know how to derive it, right? If we know how to rewrite the function so that we could easily take the derivative. But if we don't know how to do that, then we're stuck. So practice those steps so that if you ever forget the formula, if you ever forget the pattern, you can derive it yourself. So pause the video, go ahead, give those a shot, and then we'll jump back in. Okay, so this first one, pretty straightforward. We only change the base. Let's rewrite the function. F of x is equal to e to the power of the natural log of 5 to the power of x. I can rewrite that as e to the power of x times the natural log of 5. If I then take the derivative with respect to x, that's going to give me f prime of x is equal to e to the power of x times the natural log of 5 times the natural log of 5. And of course, that's going to give me the natural log of 5 times 5 to the power of x. So pretty straightforward. This next one's a little different because we have a negative sign. And we're going to want to use the derivative property where we can factor out the coefficient outside of the derivative operator. So let me show you what I'm talking about. F prime of x is equal to d dx of negative 2 to the power of x, right? But I can factor out that negative 1. So I can have negative 1 times the derivative of 2 to the power of x. And then you'll notice, right, we've already evaluated this once in this video. We did it with our opening problem. If you leave the negative sign in there, you might run into some issues because you might end up with the negative sign inside of your natural log. We know the input to a logarithmic function cannot be, it has to be positive, so it can't be negative or 0. So you may run into some problems there. even if you don't make that mistake and you keep it outside, it still just becomes more tricky to work with. So factor it out first, using the properties of derivatives that we know of, and just makes your life a whole lot easier when doing this. I'm not going to go through all the work again for this derivative. We know that's going to be -1 times the natural log of 2 times 2 to the power of x. So just negative natural log of 2 times 2 to the power of x. Okay, so again, that little algebraic manipulation of rewriting our function using e and natural log really makes these derivatives pretty straightforward, as long as we remember it, right? If we forget it, we may be stuck. But if we understand the properties, we may be able to even derive it if we're sitting there confused on a test or a quiz. So let's go ahead and fill in this box. If f of x is equal to a to the power of x, where a is greater than 0, then f prime of x will be equal to a to the power of x times the natural log of a. So it's whatever your original function is times the natural log of the base. If we need to implement a chain rule, so if f of x is equal to a to the power of g of x, right? So if our exponent is not just an x, maybe it's a 2x, maybe it's an x squared, well, then we just have to multiply by that derivative. So f prime of x will be equal to the same thing we have up here. Let me do some color coordination here. Right, so the same thing, but then we just have to multiply by the derivative of our inside function. And again, notice we're doing the same thing up here, right? It's just that the derivative of our inside function here, derivative of x is just equal to 1. So it's still a chain rule. We just may kind of skip over that part in our brain, right? Because we know the derivative of x is 1, so it doesn't really stick out to us. But if that exponent is something else other than x, then we do need to multiply by that derivative. Okay, real quick before we move on to logarithmic functions, let's just make sure that this formula also holds true for the natural exponential function. Natural exponential function. I could just say e to the x, that would be easier. Because when I gave you this derivative, right, there wasn't a formula. I just told you that dx of e to the x was equal to itself. But let's show or see if this formula we looked at for all the other exponential functions holds true for e to the x as well. Well, if we look at our formula above, we get our original function times the natural log of the base, right? So this would be times the natural log of e. Well, if I simplify the natural log of e, that just gives me 1. So this formula does indeed still hold true for e to the x. And it should, based on the conditions we gave up there, right? We said as long as our base was greater than 0, and e is somewhere around 2.7, so our base is greater than 0. Okay, time to move on to derivatives of logarithmic functions that are not the natural log. I give you a hint here. I say apply the change of base formula to first rewrite the expression below using the natural log. Because again, if we just look at this function, we may not really know what to do as far as how to take that derivative. But pause the video. If you don't remember the change of base formula, maybe go look it up on Google or in your book or whatever, and see if you can rewrite f of x using the change of base formula, using the natural log. That's important. We want to choose that as our base, we want to have e as our base, so we're going to use the natural log. And then see if it becomes more clear how we could take this derivative. So give that a few minutes of work. Okay, so if I'm going to rewrite this function using the change of base formula, I'm going to get f of x is equal to the natural log of x divided by the natural log of 2. right? So you take the ratio of your input to your log function over the base of your log function. And you can pick whatever log you want, right? You could do, I could rewrite this as f of x is equal to log base 9 of x over log base 9 of 2 again. Why you would want to do that, I don't know. But you could, right? You can pick any base for your log. Could be useful in other mathematics. I just can't think of an example of when. Now that we have our function expressed in terms of natural logs, we should be able to go ahead and take a derivative here. One thing that may help you is to even rewrite it one more time. So 1 over the natural log of 2 times the natural log of x, because that really solidifies the fact that this 1 over the natural log of 2 is just our coefficient, right? It's our coefficient of the natural log. It's just like having, if we had g of x is equal to 5 times the natural log of x, right? It would be a pretty straightforward derivative. A weird coefficient, I say weird because it looks different, right? But it just acts like a regular coefficient. So if I want to take this derivative, f prime of x, well, that's going to keep my coefficient there. So 1 over the natural log of 2 times the derivative of the natural log of x. Well, that's just 1 over x. If I simplify, I get 1 over x times the natural log of 2. And you may say, well, this looks pretty similar to just the derivative of the natural log of x. And it may be even more clear if we look at this step right here before we simplified. Right? The derivative of the natural log is just 1 over x. Well, we just have this part right here that we're multiplying by 1 over the natural log of 2. And notice that 2 was our base of the log function that we started with. That was obviously not a coincidence. So you can pattern match here. You can just try to memorize the formula. Again, because you're not going to take a ton of derivatives of log functions that don't have base e, so using the natural log, you're probably not going to just have that formula memorized, at least not as well as other ones. So it's important to know these algebra manipulation techniques, right? Knowing how to use the change of base formula. If you know how to use that, you're not stuck on the AP exam. You're not stuck during a quiz or whatnot just because you forgot the formula. You can always kind of get to it yourself using previously learned mathematics. Okay, let's jump down to our box for derivatives of logs. Given f of x is equal to log base a of x, well then f prime of x is going to be equal to 1 over x times the natural log of a. Or, again, we might have to employ the chain rule here. If our input to the log is a function other than x, so something more complicated, well, then we're just going to multiply everything by g prime at the end, right? Everything's going to stay the same, right? If we just consider this as g of x, well, then chain rule wise, we multiply by the inside function, so we have times g prime of x, and that's what we're looking at right here. Okay, that is going to do it. You actually know what? Let's do one together of a true chain rule where the inside function is not x, and then we'll be out of here. Let's actually do a product rule as well while we're at it. So we're going to do the one on the right here. Pause the video, take your time, work yourself through it, and come back and see if you did it correctly. Okay, so again, we do have a product here because it's x times 5 to the power of 2x. So I'm going to take the derivative of x, which is just 1 times my other function, so 5 to the power of 2x, plus x times the derivative of 5 to the power of 2x. And now we actually have to employ the chain rule here. Well, we're going to get the natural log of our base, so the natural log of 5, times 5 to the power of 2x, times the derivative of 2x, which is just 2. Then we're going to go ahead and simplify everything. So f prime of x is equal to 5 to the power of 2x plus 2x times the natural log of 5 times 5 to the power of 2x. And they may factor out the 5 to the power of 2x, right? You may see the multiple choice answer look like this. In fact, you probably would see it look like that. They do like to factor for their final answer. But obviously, both of these are equal to the derivative as well. Okay, that will do it for this video. As always, enjoy the rest of your day, and we will look forward to seeing you next time.